Okay, so we saw the 3 steps of sampling, quantization, and coding, but we haven't really looked into this coding, so how we then actually transmit the individual bits, the zeros and ones. Because we have our analog signal, music for example, we do our sampling, following Nyquist, that's nice, quantization, then we map this onto codes, then we have our zeros and ones, but still we cannot squeeze zeros and ones over the medium. So we have to code them. So the question for now is, how do we actually transmit our zeros and ones on the medium? And there are 2 basic principles. One is called baseband. Baseband, that means nothing but we take the digital signal. So we saw an example, so this is a 0 and this is a 1 and a 0 again and 1 and 1 and 0. So 0, 1, 0, 1, 1, 0, just an example. And bring this on our medium. So for example, we apply 5 volts and 0 volts on a copper wire. So pair of wires, because we always need a current maybe. So okay. So digital data is transmitted as it is over the medium. So data encoding, yeah, we still have to know what how is a 0 represented. For example, a 0 volt and a 1 is represented as 5 volts. And this is then what's called a cable or a line code. And this works over media that allows the transmission, in this example you see, from 0 Hertz, for example, to, let's take a twisted pair copper wire, up to 600 megahertz. So that's baseband. So you have a certain bandwidth that goes from 0 to a upper frequency. So that means the attenuation here is pretty low, and the attenuation then goes up somewhere here. So it's not a sharp cutoff, but that's how it looks like typically. That's nice. That works for example, copper wire, but that doesn't work for fiber optics. Fiber optics, or especially for all wireless communication. There we talk about broadband transmission. What does it mean? We take our digital data and do not transmit it as it is, but we have to modulate it. What this is, I will explain. So we have to modulate it onto a carrier analog signal. So we use our digital data to manipulate a carrier. So what is the carrier? So typically we have a carrier, for example, a sine wave at a certain center frequency here. And then we can do some manipulation here. And for example, depending on the data, we can lower the frequency or increase the frequency, whatever. And as we'll see, all these manipulations, they result in a signal that occupies a certain bandwidth in the spectrum. And here we can also transmit our data, because we learned, okay, if we sample, etc., 2 times the higher frequency of H minus lower frequency. Okay, fine, perfect. We can squeeze in our data here. But we have to do something. So these are the 2 fundamental methods we will have a closer look at. So baseband, that's typically inside a computer, in your chip. So you have different voltages applied, and then we code the 0 as 0 volts and the 1 as 1.1 volt or whatever. Also local area networks, they quite often use baseband. Broadband, this way use all optical networks, radio networks, cable distribution systems, etc. So first, baseband. Well, okay, we have to code our ones and our zeros. And this is how this can look like. So we directly apply this digital signal on a cable, knowing that, okay, if we transmit it, it will not look that nice. Maybe inside a computer it still looks close to this blue line, but in real cables it's rather looking like the red line. And we have to take care that the noise is not too strong, so that we do not flip bits. But as you see here, if we insert a certain threshold, we still see, okay, that's obviously, for example, a 0, that's a 1, 0, 1, 1, 0, 1. Perfect. Although we have noise, it works. So this is also called a unipolar encoding. If we have a positive voltage representing the binary 1 and a 0 indicating the binary 0, there are also what's called bipolar encoding, so where you have the binary 1 alternatively encoded as positive and negative voltage. And I will show you some examples. So what is important is we have to create robust signals. So we have to be able to tolerate distortion, as shown here. It should also be efficient. So we try to squeeze out the highest possible data transmission rate. And yeah, we can code in different ways. And depending on the coding, we can squeeze more or less when it comes to the data rate. So we can have 2 states, 3, 4, 5, whatever states. We saw this already with our multi-level signals. These are exactly the multi-level signals which we can apply as baseband signal on, for example, our copper wire. If we have a cable code, it should not only be robust and efficient, and we will see different efficiencies, it should also allow synchronization. Because here on these examples, it looks nice. So, we assume somehow the receiver knows where T and 2T, etc. is. So the receiver knows where it can sample the signal. But how should the receiver know? Inside your computer, this is very simple. Because inside your computer, if you have a computer chip, you always have a clock line, and this clock line is distributed all over your chip, and so all components know exactly when is the rising edge of your clock and when is the falling edge of the clock. So you have a clock distribution tree or several of them. Yeah, it's also complicated, but that's basically how it works. So the components know this, and then they know exactly when to sample. So flip-flops, when to sample the signal. You have a clock. If you have a local area network, well, you don't want to have a separate clock line because that's too expensive. You don't want to have an extra copper wire just for synchronization. So we need something that automatically, that's the ideal case, automatically encodes the synchronization into the signal. And in an ideal case, the positive and negative signals should alternatively arise. That's the ideal case. And we want to avoid this direct current. We learned this. We don't like direct current. So there are different ways of coding. And some of those codings, they allow for the synchronizations. And some others do not. So examples. So the most simple approach is called non-return to zero. Non-return to zero, that means, this is what you know from computers, inside chips, etc. These are the examples I showed you several times now. We, for example, encode 1 as a positive and 0 as a negative voltage. We can also say 0, we can encode, and that's typically in computer chips. We have 0 volts for the 0 and 1.1 volts for the logical 1. So that's one way of doing it. Okay, that's very simple. You can do this inside CPUs because it's very simple, and so that's quite nice. And if you can increase the data rate depending on the clock, and so this is what the computer chips do. They can increase data rates if they speed up the clock. So nice. The disadvantage is, how do we synchronize? How do we synchronize, especially if we have longer sequences of zeros and ones. So how should I know that now a new bit follows? So the receiver has to be synchronized, and it's very simple to synchronize if you have the edges. You sync on the edges, and then you know if you have these 10, 10, 10 patterns, it's easier to synchronize. But if you have long sequences of zeros and ones, you will lose synchronization. This is not a problem inside a chip because, as we learned, we have these separate clock lines. So the clock distribution tree telling all the components inside a chip where the edges are. But in a local area network, the receiver doesn't know anything. So the receiver has to be synchronized. But if we just use a simple non-return to zero code, we cannot synchronize the receiver. So there are other ways of doing it, so-called return to zero codes. So what does it mean? The signal returns to zero between each pulse. These signals are self-clocking. So what does it mean in our example here? So a 0, for example, is minus 5 volts, and then we return to 0 volts. Plus 1 volt, and we return to 0. And if we now have longer sequences of ones or zeros, we still have the edges here to synchronize. We always have an edge. That's nice. We don't have direct current, and it's a self-clocking code, return to 0. The problem is we need twice the bandwidth. Why? Well, look, for example, here coding the 1. We have here one transition from 0 to plus 5 volt and another one from plus 5 volt to 0. Then, depending on the following signal, we again have a transition here and a transition there. But per interval, we have 1, 2 transitions. 2 transitions per interval. If you compare this with a non-return to 0 code, this would be 0, 1, 0, 1, 1, 0, 0, 1. We only have 1 transition per bit. So 2 transitions per bit. That means we require twice the frequency to represent this signal. That means we need twice the bandwidth, following Nyquist. So that's a problem. So if you have this classical coding with 10 megabit per second using non-return to 0, well, we now need twice the bandwidth because we have now 20 mega changes of the signal using return to 0. Okay, we'll come back to this problem. So return to 0 has a problem. There are many more ways of doing this. I just give you some examples. For example, differential non-return to 0, similar principle to non-return to 0. But we encode now 1 as a voltage level change, and 0 we do not change. You see here, no change because a 0 follows. Here we change because a 1 follows. Here we change because a 1 follows. So this helps a bit, but we see here the disadvantage of we go out of sync is now only for sequences of 0s, 2, and sequences of 1. Well, because we change the voltage level for each one, we have solved the problem. Okay, but still, for long sequences of 0, we have a problem. So, but these are the line or cable codes we can use, just some examples for on wires with their disadvantages. But we need synchronization, so we have to solve the problem. And one solution that is the so-called Manchester code. There are different versions of Manchester codes, and the Manchester codes, they were quite famous in the context of Ethernet. We'll come back to Ethernet when we cover the layer 2. So the idea here is that we transfer the bits by the edges in the middle of each bit. So, and we code, in this example, we code a 0 by a falling edge, and we code a 1 by a rising edge. So we do not encode our data into the levels, but in the direction of the edges, falling edge or rising edge. So falling edge, rising edge, rising edge, falling edge, falling edge, rising edge. And then, okay, we simply connect these. Okay, no problem. Oh, oopsie, we cannot connect. So there must be a falling edge in between so we can connect. Okay, fine. Oops, there must be a rising edge in between so we can connect and create the signal. So there are additional edges in between. So we code everything as falling and rising edges. So that's the idea. So for example, and we insert these edges if required. Big advantage is here, we have definitely always an edge here at the frequency of our bits. Definitely. That's great. So this helps for synchronization. So we know, okay, that's always the middle of a bit. There's no direct current, and we immediately notice end of transmission if nothing is going on, because then we have 0, for example. So that's nice. But again, due to the fact of this insertion of these helper edges, let's call them this way, we again require twice the bandwidth. So, because it could be the case that you transmit a long sequence of zeros and ones, this creates twice the bandwidth, or assuming the same bandwidth, capacity is only half. There are some versions for this, so differential Manchester, so that's basically a Manchester code. And now you encode 1 as a missing voltage level change between 2 bits and a 0 as voltage level change between 2 bits. So, and there are many more versions for this, but in the end we always have the problem that you can create twice, well, double the frequencies requiring double the bandwidth. So the efficiency of this, assuming the same max bandwidth of a cable, is only 50%. That's the problem. It's only 50%, so basically you waste bandwidth due to this coding. So non-return to 0 doesn't waste anything, but you cannot synchronize. We learned long sequences of ones or zeros. Well, they don't allow synchronization. Here Manchester allows synchronization, but the efficiency is only 50%. So going to non-return to 0 with 100% efficiency sounds good, but no sync. Problem. So 100% great, but no sync. So we need synchronization. Here we have sync, but only 50%. Also return to 0 provides a synchronization, but only 50%. So that's a problem. So we need something in between. So we have to spend some capacity for synchronization, but maybe not 50%. And this was the idea of the, in this case, 4B, 5B code. So the efficiency, 50%. We can also call this a 1B, 2B code. So 1 bit is coded in 2 binary symbols. Not efficient. 1 bit in 2 symbols, because we need this additional edge. So the idea is, why not combine, because we are digital anyway, why not combine 4 bits and code them as 5 bits? How does it help? Well, the idea is, for example, and we learned this with the differential non-return to 0 code, we have a level change at 1, no level change at 0. Oh, warning, alarm, no sync. We learned that we have no synchronization then with this long sequence of zeros. So we have to avoid long sequences of 0. Long sequence of 0, that's a problem. Okay, what we do is we map now 4 bits, whatever, onto 5 bits. And we construct the 5 bits in a way that no matter how we concatenate these 5 bits, we never have a long sequence of zeros. That's the idea. Because we map 16 different words, 4-bit words, onto 32 different words, we can select out of these 32 those, when concatenated, do not create too long sequences of zeros. And here for the 4B, 5B codes, it was made in a way that we have maximum 3 zeros in sequence. And as we now map from 4 to 5 bits, we have some additional combinations that are not valid data symbols, but some additional commands, for example. It works as follows. So we group 4 bits, map them on these 5 bits. And as you see here, for example, we map this 1010 to 10110. And no matter how you now combine these data values, no matter how you combine them, you will never have more than 3 zeros. So for example, if you transmit E, and no, it's not the letter E, but this represents this value 11100, and then after that, for example, 4, okay, you have exactly this maximum of the 3 zeros. So no matter what data you have, you can now use your non-return to 0 in this differential way. For example, you avoid the zeros. Perfect. So we can always have enough information for clocking, for the synchronization. Plus, we have, and this is just a part of them, there are some more words, code words here that represent something special. For example, end of transmission. Even you can even cut the wire, then it's only zeros if you cut the wire, and this also indicates the receiver, oh, okay, now it's quiet, nothing is going on. So that's the idea. And this was introduced with a technology called FDDI, Fiber Distribution Data Interface, in the 80s, already offering 100 megabit per second at that time, pretty fast. And FDDI not used anymore, but the ideas of 4B, 5B, they survived, used in USB, in fast Ethernet. Now, for example, 8B, 10B, gigabit Ethernet or PCI Express, or new versions use 128-bit mapped onto 130-bit. And this is used, for example, in 10 gigabit Ethernet and also PCI Express versions. So you see, the basic idea is always the same. You map some bits, so group of bits, into another group of bits, using more bits. That gives us you the freedom to manually design those bit patterns, in this case, to avoid long sequences of 0, maximum 3, but never 4. That was the idea here. Plus, it gives you the opportunity to have some extra code words for signaling start and end and whatever, idle and things like this. Okay, so that's the idea. To summarize this, we have learned the relationship between bandwidth, baud symbol rate, bit rate. Please remember, bandwidth is a property of the medium. So you transmit with a certain low attenuation, a part of the spectrum over the medium. So that's the range of the frequencies, part of the spectrum. That's the bandwidth. We also learned bandwidth requirements of certain signals. And this has to match. We learned what the baud rate is, so how many symbols per second we transmit. And these symbols are samples of a signal, and they carry a piece of, in the end, information. If we go to information theory, so some information. For us, it's data. And depending on how we modulate, and we'll see some more examples, we can determine how many bits we transmit per symbol. We saw very simple ways of coding, return to 0, for example. We need 2 symbols per bit. We saw non-return to 0, 1 symbol per bit. We saw multi-level signals, several bits per symbol. And we can easily calculate our data rate in bits per second. And that's really the amount of data we send over a channel. And that is basically how many symbols per second we transmit and how many bits per symbol we code. And this gives us the bits per second. So please distinguish between symbols and symbols per second, symbols representing certain samples, and the data rate in bits per second. And you should also know how to relate this to the bandwidth of a medium and to the bandwidth requirements of signals. So some questions. So what is the difference between a line or cable code and broadband transmission? You should have understood the basic ideas. Inside computers, we learned that, okay, line code, non-return to 0 is a very good choice, but for communications, that's a problem. Why? Why does this work inside a computer, inside a chip? Why not for communications? And then a big question is, how can we achieve synchronization? I've shown you different ways how we can synchronize senders and receivers. Receivers have to be synchronized, otherwise we do not know where does a bit start. When should we sample the value we receive? Because there's this, shaking signal coming in, but when do we say, now we sample? And you should have also learned the basic ideas of 4B, 5B, 8B, etc., etc. What is the idea behind this?